Welcome! Today we're going to do some applied optimization problems. They tend to just be story problems is all we're doing. So, remember, if you want to maximize a function f on a closed interval a to b, our procedure was to find the critical points. Remember, these are usually the places where the derivative is 0. And then the endpoints, so that's x is equal to a and b. And then you make a table of them, and you see who's biggest. The biggest is the max, the smallest will be the minimum. All right, so as I said, these problems are usually story problems. So here is the first example. Say I've got a wire of length L. You can say meters, kilometers, inches, I don't care. Anyway, I want to make a rectangle from that. And I want to find what are the dimensions to give me the maximum area. All right. Okay, so these problems tend to follow a familiar pattern. And the first step is pretty much always to convert the word problem into math. Important parts that usually go into this, usually you have to label things, which is often equivalent to saying you have to name variables. And it's not always the case, but often you'll end up doing this best by drawing a picture. But you certainly are always going to have to name variables to get started. All right. So we had this piece of wire of length L. We were going to make it into a rectangle, like that. And so to even talk about the dimensions of this rectangle, I would need to label things. So let's count the bottom as x and the side as y. Then the thing that we want to maximize is the area function, which will just be x times y. But there is a constraint here. X and y aren't independent of each other because this wire was length L, so the perimeter of this rectangle has to be L. So I must have 2x plus 2y, that's the perimeter, being L. So I want to maximize the area subject to 2x plus 2y equals to L. All right, now we've converted it to math. We have enough variables. But in this case, we have too many variables. We're expecting to do some single variable calculus, probably a derivative down the line, but we've got x's and y's here. So when you have too many variables, then we want to get rid of one. Okay, and that's the case here. Too many variables, want to get rid of one. But this equation here tells us the relation between x and y. So we can solve for y, for instance, in terms of x, and then remove that from the area. So 2x plus 2y equals to L. We can solve that for y. So we would take L and subtract 2x from both sides of that equation, and then divide by 2 to get y. And we care about that because we can insert it up here into the area formula. So we get area, which was initially xy, now will be x times this mess. L minus 2x all over 2. So I'm going to write that as x times L over 2 minus x, and I'll multiply it out further, L over 2 times x minus x squared. So now we have a formula for area, and we're down to a single variable. So we're now just going to maximize this function, but we have to figure out on what interval to maximize it. So looking back at the problem here, way back at the beginning, the smallest x could be was 0. Doesn't make any physical sense otherwise. So here we're going to find the interval. Well, we know, of course, as I just said, that the smallest x can be is 0. How big can it be? Well, the maximum, if we had everything going into x, all of this wire, imagine taking the rectangle and shrinking it down, the y smaller and smaller and smaller and smaller and smaller, until the wire just double loops on the base. And that would be the biggest x could be. So if I'm double looping L, just bending it in half to make x, that would be L over 2. So the biggest x could possibly be, would be L over 2. All right? So the interval will be 0 to L over 2. All right, now that we know the function and we know the interval to maximize it on, it's just calculus time. So for calculus. So we want to maximize this function a, which was L over 2x minus x squared on the interval 0 to L over 2. Okay, step 1 was to find the critical points, which means we had to solve the equation 0 equal to a prime. So where's the derivative 0? But the derivative, if we take it with respect to x, is just L over 2 minus 2x. So that means we have to solve this. 0 is equal to L over 2 minus 2x. So throw the 2x to the other side, and then divide by 2 on both sides, and you get L over 4. So that's the solution, and only one critical point. And then, remember, we made this table where you put all the critical points here and the endpoints. So the critical point was L over 4. The endpoints were 0 to L over 2. And then you had to plug them into your function. And the function was L over 2. Well, let's factor out the x. X times L over 2 minus x. All right, so if I plug in L over 4, I get L over 4, and then L over 2 minus L over 4. So that's another L over 4 there in the parentheses. So I get L over 16. If I plug in 0, I get 0. And obviously for that I plug in L over 2, I get 0 as well. So this is the max. So now you can write down the answer. The maximum area is, we saw L over 16, and you get it when x is L over 4. All right. Now, I suppose you should say what y is. Remember, 2x plus 2y was L, so you can plug in x into there and solve for L. But anyway, if you do that, you'll see that the y has to be L over 4 as well. So actually you maximize the area by making a square. All right, that's it for our first example. See ya.